Hello everyone. I'm Meghana Yeluri from Cleveland State University. My topic is Revolutionizing Ultra-High Performance Concrete, Unleashing Metakaolin and Diatomaceous Earth as Sustainable Fly Ash Alternative. So as we all know that UHPC is an advanced construction material with exceptional mechanical and durable properties. UHPC always possesses high compressive strength, often exceeding 20,000 psi, and high flexural performance and ductility, which allows it to withstand deformation, structural deformations, and bending without any fracture. UHPC aims to achieve densely packed particle arrangements to achieve its dense microstructure and enhance durability and resistance to various forms of degradation. UHPC isn't just functional; it is architecturally pleasing, making it more suitable for architectural applications. The most adaptable definition of UHPC is given by ASTM C 1856. According to this, the compressive strength of UHPC should be at least 70,000 psi, with a flow ranging between 8 to 10 inches, and the maximum size of the aggregate should not exceed more than 1/4 inch. Because of its exceptional properties, field cast UHPC finds its application in various construction projects such as connection of prefabricated bridge elements, closure of pore spaces in pile caps, overlays and repairs for bridge decks, and as grouts for bridge shear keys. UHPC is also tailored in achieving architecturally pleasing elements such as architectural elements because of its ability to cast into intricate shapes. Apart from its infrastructural applications, UHPC is also used for nuclear applications such as grout for encapsulating radioactive waste. The primary SEM used in UHPC is silica fume, which is very expensive among all the other SEMs in North America. Therefore, it is often replaced with inexpensive class F fly ash. But unfortunately, the future availability of fly ash is also uncertain because of the closure of the coal power plants. Here we can see the decreasing trend on the production of fly ash from 2010 to 2020, despite of its high demand. Therefore, there is an urgent need to find a cost-effective and environmentally friendly alternatives for fly ash. Therefore, in my research, I choose to select Metakaolin and Diatomaceous Earth as sustainable fly ash alternatives. In this research, local sand confining to ASTM number 4, type 1L cement are used, class F fly ash and Diatomaceous Earth, silica fume SF100 and Metakaolin MK 828 from Master Builders are used as SEM, polycarboxylate based HRWRA Master Glanium 3030 from Master Builders is used in my research, and also steel fibers with an aspect ratio of 65. Throughout my research, 2 curing regimens are investigated. The first one is moist curing, in which the specimens are kept in the moist curing room at a temperature of 23.5 degrees Celsius until the day of testing, and the warm bath, where the specimens are subjected to 90 degrees Celsius until the day of testing. To produce the UHPC mixtures, our target was to achieve an average static flow between 8 to 9 inches and a minimum compressive strength of 17,000 psi. Various trial batches were made by varying HRWRA dosage with a constant water-to-cementitious ratio. The control UHPC is given a designation SF8FA8. That means it has 8% of silica fume and 8% of fly ash out of total cementitious materials. The further optimization was focused on replacing this fly ash with Metakaolin at different replacement levels. from 0% to 100% in the increments of 25%. For example, SF8 in mixture SF8, FA6 and MK2, the mixture has 25% of replacement with fly ash. Similarly, the diatomaceous earth was modified UHPC mixtures were also optimized. During the optimization process, it was observed that the HRWRA dosage has been increasing with the increasing content of MK and DE powders. This is because of the lack of ball bearing effect produced by the fly ash particles. In MK modified UHPC mixtures, the highest strength was achieved at in the mixture SF8, FA0 and MK8, which is 100% replacement of fly ash, and the highest compressive strength is 20,210 psi at when cured under WB curing regimen, which is 2.2% more than the control mixture. In DE-modified UHPC, the highest compressive strength was achieved when cured under WB at 75 replacement level, but at 100% replacement level when cured under WB, the compressive strength was 19,690 psi. Therefore, it was opted as our final mixture for further investigation because our goal was to replace fly ash completely. Here we can see the compressive strengths the effect of SEMs on the compressive strength in both the curing regimens MC and WB at various ages. In moist curing condition, the compressive strength was increasing with age, whereas the rate of hydration was decreasing. The strength gain in fly ash, the strength gain in control mixture was faster than in modified UHPC mixtures. At 7 days, the compressive strength in all the three mixtures showed similar results, and there was a substantial increase in the compressive strength from 7 days to 28 days in moist curing condition. In warm bath curing specimens, the 90% of its 56 compressive strength was attained by just 3 days, and there was no marginal strength or a little strength gain of less than 10% after 28 days. At 56 days, MK mixtures showed better performance than control mixture by 3.5% and DE mixture showed just a 1.7% decrease when compared to the control mixture. And WB and in WB and MC regimens, the 56-day compressive strength was similar with less than a difference of 5%. Coming to the flexural strength, control mixtures performed better than the MK modified modified UHPCs. At 7 days, MC cured specimens exhibited greater flexural strengths than in WB cured specimens. At 28 days, the flexural strengths cured under WB showed improved performance, and the MK and DE modified UHPC mixtures at 28 days showed an increase of 26% when compared to 7 day strengths. These are the load deflection curves which I have used to calculate the MOR, peak, toughness and residual strengths at L by 150 and L by 600. The highest toughness value was exhibited by MK mixture at 28 days when cured under WB, and the MK mixture also showed better results results for the residual strength at L by 150, whereas the DE had the least residual strength. The similar trend was also observed in residual strength at L by 600. Except in the case of 28 days MC curing and 7 days WB curing. In 28 days WB, the DE specimen had residual strength nearly 1% greater than the control mixture and 3.5% more and in 7 days warm bath curing, DE specimen showed 3.5% increase when compared to the control mixtures. The split tensile strength was conducted on moist curing specimens at 28 days, and the split tensile strength of MK and DE-modified UHPC mixtures reduced by 15% and 33% respectively. To study the shrinkage characteristics of the UHPC mixtures, 3 curing regimens were investigated. One is air-dry condition, in which the specimens are subjected to air until the day of testing, that is 56 days, right after demolding. The MC-dry condition is where the specimens are kept in a moist curing room for 3 days, and then they are left in the air until the day of test, until 56 days. And in moist condition, the specimens were kept in a moist curing room for 56 days. We can see that in moist condition, MK and DE-modified UHPCs performed better than the control mixtures by 27% and 25% respectively, whereas in air-dry condition and MC-dry condition, MK shrank less by 29% and DE shrank more by 8.4%. And in MC-dry condition, MK shrank less by 13% and DE shrank more by 44%. So these are the surface resistivity of all the UHPC mixtures conducted on the 4x18 cylinders. According to ASHTO specification, the surface resistivity has been increased with age in all the UHPC mixtures. By the 7 days, MK modified UHPC reached very low chloride ion penetration susceptibility, and by 56 days, control and DE reached the very low chloride ion penetrability. I can say that by 56 days, MK reached the negligible chloride ion penetrability, whereas the other 2 mixtures were in the range of very low chloride ion penetration. These are the freeze-thaw durability results. We can see that there was no change observed in relative dynamic modulus, and there is no mass change was observed until the 300 cycles. So these are the conclusions. The Metakaolin and Diatomaceous Earth were investigated as alternative cementitious materials to fly ash. 2 curing regimens were investigated. MK modified UHPC had greater compressive strength when compared to the control, and DE-modified UHPCs showed similar results as control, maybe less than 1% approximately. The flexural strengths were greater than control mixtures in MK and DE-modified UHPC when cured under WB for 28 days, and the shrinkage was less than 1000 microstrains in all the curing regimens. All the mixtures exhibited very low chloride ion permeability and excellent freeze-thaw resistance durability was observed. Therefore, by this I can conclude saying that both MK and DE are viable substitutions for fly ash because MK and DE modified UHPCs demonstrated desired flow values for UHPC and comparable mechanical performance. Thank you for giving me this opportunity.